Okay, so let's do some arithmetic in Python. We're at section 2.3. So these are all the arithmetic operators. We'll know them from math class, and let's say we have addition, subtraction, multiplication, exponentiation. We also used to call them power, like 2 raised to power 3 is 8. Here we see an example, x raised to the power y. Okay, so let's say x has been assigned 2 and y has been assigned 3. So this expression will evaluate to 2 to the power 3, which is 2 times 2 times 2, which is 8. We could also find, we could also divide two variables. There is another type of division called floor division. I'll explain what that is. And then we can also find the remainder of a division in a division operation. So, so let's take an example of the first one. I mean the multiplication. Um, can do addition first. That's all that we need to change. But let's say we multiply 7 with 4. The result is, of course, 28. Exponentiation 2 raised to power 10. I could do it easy. 2 raised to power 2, which will give us 4. Okay, now you can do 2 to the power 10, which will give you 1024. Another one is, okay, this is one way to find the root of a number. So for example, 9 raised to the power half, 1 over 2. This will give us 3. There's another way to do it. Let me insert a new cell here, although we haven't done this yet, but this will help if you can remember. Let's say I import the math library and gives me a lot of function, for example, sine, cosine, power, square root, and so on. And if I use a function from this library called square root, SQRT, and I give it 9 as an argument, I'm going to get the same result. Only for square root, which means your power in the square root is always half, which might not always be the case. That's why you need to know this exponentiation operator. For example, if I take 9 raised to the power 2, I'm going to get 9 times 9. Similarly, another operator, arithmetic operator, is division. Let's say we're dividing 7 by 4, so you're going to get 1.75. There is another type of division called floor division. How it is different from the true division. So let me explain it here. Assume we're having 7 and we're going to divide it by 2. Okay, so the remainder is 0 and the quotient will be 3.5. But the floor division never takes the fraction part. It only takes the whole part. So it will truncate that, round it off to the floor. That means to the smallest integer. Okay, 3. But if it was 8, we would divide 8 divided by 2, then the quotient and the quotient would be 4, which would also be the result. The true division will give us the same number as the floor division. So the floor division is only different if the number involves the fraction part. So that's how the floor division works. If for the floor division in Python, we use double forward slash. For example, if we do the same 7 divided by 2 here, we're going to get 3.5 here. But if I did the floor division. So if I do it here, I'm going to get 3.5. But if I do it here in the floor division, I'm going to get 3. But if it is 8, then it should be 4. In fact, both in this case will give me the same result. Okay. Similarly, 3 floor division, or 5, is 0 because we know that the result is less than 1. And if we divide 14 over 7 in floor division, we're going to get the same result as the true division would give us. So that's a true division versus the floor division. So the floor division truncates the fractional part. whatever is after the decimal point. Similarly, we can try here. The 13 in true division, negative 13 would give us 3.25, but in the floor division, it would give us a negative 4 because that is this smaller than the true division. So the result of floor division always will be smaller than this. It's a little tricky here because it looks like we'll get only minus 3, but minus 3 would be greater than minus 3.25. So that's why we're not going to get negative 3 here. We're going to get negative 4. There is always a case possible in math in which division by 0 occurs. We know that in mathematics that's not defined, and that's also the Python will tell us that the division by 0 is triggering at it as an exception. Okay, so it's not allowed and results in an exception. So take it as like an error. It's called the zero division error. Our program should always find ways to how to deal with the division by 0 situation. If it is going to occur, we're not gonna proceed. So there is a concept called as exception handling, which we will learn later in the course, in which I'll tell you more about how to deal with these kind of exceptions. Similarly, you might be triggering another exception if you are adding 7 to something which does not exist. Remember, we did not use z anywhere. We never assigned any value to z, and that's why. So if that's why we are getting an exception. Okay. So for example, this time if I assign a value 5 to z and I initialize it, and I know a variable now with the name z does exist in the computer memory holding a value 5. Now, if this time I want to add 7 to it, the Python will not complain because z does exist. But if z was not there, let's say another variable s is not there, and I'm gonna add something to it, then an exception will occur. Then it will say that s is not defined. Okay, so you're using a variable that you have not yet created. So exceptions produce tracebacks. The line that begins with these dots, this one, okay, shows the code that caused the exception. So this is the only line here, so it's pointing to that line, but there might be a situation in which we have 100 lines and in which only one of them is causing exceptions. So we'll see the traceback and we'll trace back the code and reach out to the exact point which triggered the exception, which caused the exception. Okay, so we always should have this kind of like the practice of understanding these tracebacks because they help us debug our code. They help us catch the exceptions in our code. Okay, so a good practice is to always initialize variable, create the variable before using it, so that you never see exceptions. There's another operator called remainder operator. In some texts, it's also called modulo operator. So if you saw the division here, so if for some reason you're interested in the remainder and not in the quotient, then instead of using the forward slash, you're going to use the percent signs here. So let's say we know that 17 modulo 5 gives us 2. Why? Because if you divide 17 by 5, the quotient will be 3 and the remainder will be 2. So this is how you get the remainder. What happens in this case if you divide 7.5 by 3.5? We know that 3.5 times 2 is 7, so the remainder should be 0.5. Okay, so one thing you notice here that we always write the arithmetic expression in a straight line form using Python operators. We could group expression with parentheses. For example, if I want this mathematical operation to be done before the result is being multiplied with 10. So this is how I would do it. But let me make a duplicate of this, remove the parentheses. Then what do you expect the result to be now? Anyone? will follow the precedence of the arithmetic operators, in which division has more precedence than addition. So that, which means that 5 will be multiplied with 10 before the result is added to 3. So this will result in 53, not 80. So be very careful. If you want to enforce a certain operation, arithmetic operation to be done before the other one, enforce it through the by grouping them using parentheses. And there is no limit in putting the number of parentheses. For example, you could put it in double parentheses. Python will not complain, although you would never do that. But I'm just highlighting that use of parentheses is there's no limit on it. Okay, so if I do this, you saw already that it will give us 53. So operator precedence rule 1 of 2 generally the same as those in algebra. Expressions in parentheses evaluate first. So parentheses may force the order of evaluation. Parentheses have the highest level of precedence. An expression with nested parentheses, for example, this, the innermost will be done first and the result will be calculated and the outermost will be done later. We already know this. Exponentiation operation evaluate next. So if, for example, if we are raising something to uh, to the power, for example, 3 raised to the power 2. So this time, this 3 will be 3 um, raised to the power 2 will be evaluated first, 9 will be computed, and then that 9 will be added to 50, we're going to get 59. So after parentheses, the exponentiation get their precedence. And then it's followed by multiplication, division, and modulo operations evaluate next. And the very end, addition and subtraction operations evaluate. Okay, so as I explained, we could have redundant parentheses, and if both operands are integer, the result is an integer. Okay, normally we discussed the data types previously. So if 3 numbers are going into this, and I find the type of the result here, then the type of the result will come from the type of the operands. For example, 3 is integer, 5 is integer, 10 is also an integer. So I'm expecting the result to be integer. If any one of them is float, for example, 3.5, then the result will be float because 2 of them are integers, but one of them is float. Okay, so that's how we find um, we find the type of the result based on the operands. If both operands are floating point, the result of course is floating. Mixed type expression produce floating point results. So even if one of them is a floating point, as I said earlier, we're going to get a float as a final result. In the last example here, I'm going to solve this quadratic equation. So for those who do not remember the quadratic formula, I'm going to open it here. It looks like this. So the purpose here is not to understand this math. The purpose here is to, given this quadratic equation, it's quadratic because x raised to the highest power is 2. It's an expression of order 2. And in order to find the unknown x, we're going to use the quadratic formula. So I'm going to give you this as an example here. So let's pick the coefficients from this equation. So a is the coefficient of the x squared term. 6 is the b. Let's call it b is the coefficient of x, and c is the constant. So I've already initialized them here. So if I can insert a new cell here, so let me initialize them here. A is 1, b is 6, and c is 8. Okay, and now in order to find the unknown x, I will say that it's negative b plus minus. So I'm going to take the case of plus first, this one. And now it's the square root, okay, of b squared minus 4ac. So it looks like this, b squared minus 4ac. So I'm going to say b squared minus 4 times a times c, okay, I'm gonna raise all this to the square, to half. This will give me a square root of this term. And everything is divided by 2 times a. If I execute this now, I see nothing, but if I say display x, it's going to give me the first root, which is -2. So let's call it x1, because we need to find another root also. And let's make a duplicate of this. And this time, instead of the positive here, I'm going to take another root which involves the negative sign. So in order to find the other root, all I need is to replace this by negative. And that'll give me, and we also name this as a second square root. Okay, so if you want to present the result, the best way is the print the roots of the equation x squared plus 6x plus 8 are x equal to, or I don't need to do this, are x1 comma x2. So if I do this now, so I see the roots of the equation, of the quadratic equation, are -4 and -2. So why do I get the same um, roots? Let me find this here. So x1 is, I know x1 is -2, x2 is -4, so it should give me -2 and -4. Okay,